All right, let's dive right in. Today, we're talking about NVIDIA's Intelligent Platform Management Interface, or IPMI. We're going to break down how to set it up, how to lock it down, and how to use it to manage your hardware. And the best part? You can do this even if the main OS is completely out of commission. This is your essential guide to what we call out-of-band management. So here's our game plan. We'll kick things off with the basics. What exactly is IPMI? Then we'll get into the weeds of how it communicates over something called the I2C bridge. After that, it's all about practice. We'll run some real commands. Then, and this is crucial, we'll talk security. And finally, we'll wrap it all up with a step-by-step setup guide for CentOS. Okay, first things first. Before we can start tinkering and securing this thing, we really need to understand what it's all about. So what is IPMI, and why should you as a sysadmin care so much about it? At its heart, IPMI is basically a universal remote for your hardware. Now, the magic phrase here is out of band. That means it works on its own little island, totally separate from the CPU, the BIOS, and the operating system. Just think about that for a second. Even if your server is off or showing the blue screen of death, IPMI is still there, wide awake, listening for you. You know, the best analogy I've heard is to think of IPMI as the building superintendent for your server. It's got its own power source, its own network connection. It has the master keys to everything. It can check on the system's temperature, log weird events, or even force a hard reboot, all without ever needing the main OS to be awake. So how does our super get its information? Well, the communication pretty much flows in two directions. First, you've got the Baseboard Management Controller, the BMC, which is kind of the brains of the IPMI operation. It can reach out and pull data from the BlueField DPU. And then it can go the other way. The BlueField DPU can ask its own BMC for info about itself. Okay, let's peel back a layer and get a little more technical. All of this back and forth communication we're talking about, it happens over a special highway called the I2C bus. And just like a real highway, every car, or in our case, every device, needs its own unique lane or address to keep things from crashing. So let's look at the first scenario. Say the BMC wants to get some information from the BlueField. In this case, the BMC acts like the host, and it uses its driver to listen on address 0x20. The BlueField, which is the device in this conversation, listens on a different address, 0x30. See, two different addresses, creating a clear path for that request. Now, what happens if the BlueField wants to start the conversation? Well, the roles flip, and, this is the important part, so do the addresses. Now the BlueField's host driver uses address 0x11, and the BMC listens on 0x10. Having this total separation for each direction is absolutely key to making sure they don't talk over each other. And this isn't just a friendly suggestion, you know. The documentation is crystal clear here. If those addresses clash, if two devices try to use the same one, it's game over. One of the drivers will just fail to load, and your communication bridge comes crumbling down before you can even use it. But hey, the good news is, if you ever do need to change these addresses for some reason, it's really not that hard. You just have to pop open this one script file, find these two variables, and you can set whatever custom addresses you need. All right, that's enough theory for now. We get what it is and how it works. Let's get our hands dirty and actually start running some commands. The simplest, most direct thing you can do is query the BMC right from the BlueField DPU itself. You just use the standard ipmitool command. So for example, if you run ipmitool SDR-list, it'll talk to the BMC and spit back a whole list of all your system sensors. We're talking fan speeds, voltages, temperatures, the whole shebang. Okay, but what if the BlueField wants to check on its own status through this management system? It can do that too. It basically sends a command to itself using the localhost address. This is super useful for running standardized health checks and just making sure the IPMI service on the DPU is up and running correctly. And here it is. This is where IPMI really shines. Remote management. From literally any other computer on your network, you can use that LAN plus flag, which just tells it to use a secure network connection. Point it at your BMC's IP address, give it your username and password, and bam, you've got full out-of-band control over that server. Now, with that kind of power comes a whole lot of responsibility. So let's shift gears and talk about something that's absolutely critical: security. Specifically, let's look at why you might want to harden your system by shutting down one of those communication paths we talked about. Here's the potential problem. That I2C one channel allows the BlueField's main processor to send commands to the BMC. Now, in a high security situation, you have to work from a zero trust mindset. If an attacker ever managed to compromise that processor, they could use this channel to send their own malicious commands to the BMC, and they could potentially get full root access to the entire server. So, how do we slam that door shut? Well, the first method is the high-tech automated root. It uses the Redfish API, which is a modern standard for managing servers. Because it's an API, it's absolutely perfect for scripting. You can write a simple script that sends a request to change the setting, another to confirm it changed, tells the system to reboot, and then checks that the I2C device is gone, all without you lifting a finger. The second method is the good old-fashioned hands-on approach, going right into the UEFI BIOS. You just reboot the server, jump into the setup menu, click your way through the device settings until you find the option for I2C1 and check the disable box. Save, exit, reboot, and you're done. This is perfect for when you're setting up a single machine and you're right there at the console. So to sum it up, it really just comes down to what you need to do. Redfish is your go-to for managing a whole fleet of machines remotely and automatically. The UEFI method is for when you're working on one machine at a time and you have direct access. 2 different tools for 2 different jobs. Okay, for our final section, let's bring this all home. We're going to walk through step by step exactly how to get all of this working in a CentOS environment. First up, we need to lay the foundation. That means loading some kernel modules so the OS can talk to the hardware, and then installing some standard tools like ipmitool. But, and you'll want to pay close attention here, there's a bit of a trap. The version of I2C tools that comes with CentOS is too old. You absolutely have to go grab a newer version and build it by hand for this to work. Next, we need to get NVIDIA specific drivers installed. They come as source RPMs, which sounds complicated, but it just means you have to rebuild them. This process basically compiles the drivers, like those host and device drivers we talked about earlier, so that they match your system's kernel perfectly. It's all about making sure everything's compatible. And for the final stretch, we just need to flip the switch. We'll load the driver we just built, start up a related service, and then we enable and start the 2 main IPMI services. These are the background processes that do all the heavy lifting. Once they're running, your IPMI interface is officially open for business. So there you have it. We've gone from the basic architecture to running commands, securing the system, and a full installation. The power of out-of-band management is officially in your hands. The only real question left is, what are you going to do with it? What's the first automation script you're going to build to make your job just a little bit easier?